So let me record it. Okay, so all good now. So the first part is about reasoning as memory. Here, I will give a brief introduction of the concept. Basically, we will go through three types of memory that plays very important roles in our reasoning, which are item memory, relational memory, and program memory. Okay, for the introduction. So I think all of us agree that memory is a part of intelligence. Intelligence require memory. And basically, memory is the ability to store, retain, and record information. Human memory store item, events, and very high-level structured concept knowledge, while the memory of the computer store data and temporary variables of programs. So although they're different, but the basic concept stays the same. This all try to store, retain, and recall. Regarding the correspondence between the memory and reasoning, I think many evidence from neuroscience literatures indicate that there's a lot of similarities. For example, in reasoning, we have two processes, fast and slow. In memory, we also have similar two kind of processes, familiarities and recollection. And familiarities is very quick, while recollection of the knowledge or concept is often very slow. And many cognitive tests show that when you try to increase the difficulties of memorization tasks, then the performance of the reasoning is also reduced. And if you look at the graph here, there's always the correspondence between the performance of reasoning and memorization of individuals in cognitive tests. When we talk about memory, we often mention about its common activities. So the first activities is about storing or encoding. We need mechanism to write the information to the memory, and this often requires compression, right? We cannot write everything into a finite memory. The second ability is to retain, which means we keep the information over time. This is often assumed in machine memory, just plug in the power and it's run forever. But for human memory, it can be very hard to keep or retain the information. And finally, is the retrieve activities, which basically we recall or we retrieve the information from the memory to solve the task at hand. We can view memories from a different angle, where we classify it into different types of memory, which are item memory, store the objects or the events, variables, entities. Relational memory, store the graphs, the structure, the relationships. And program memory is store the programs or the functions, procedures, and how-to knowledge. So they are different from the content they are contained in the memory. Okay, so let's go to the first type of memory, the item memory. Here are the three prominent examples: associative memory, RAM-line memory, and independent memory. Okay, so distributed item memory can be viewed as an associative memory, and they are very common in our daily life as well as our daily tasks. For example, in language, you need a kind of associative memory to associate the concept. Like the green traffic light means go, and then red means stop. And it's often stored in the semantic memory in human brain. On time, you need some kind of episodic memory to store or to bind the event to the time on the context that the event happened. Or the object here, you store the object, the location, the password of your phone in some form of like temporary working memory, and you use this for the current task, or you can store a correspondence or association between the behavior in the motor memory. And the most, one of the most important or maybe early work on associative memory is the correlation matrix memory and Hopfield network. The idea is very simple. You can associate the item by outer product, as you can see here. You want to associate the input I and output O. You use outer product and sum them up. And after that, you have the memory M here, M hat here, which contain all these items, I and O, or B and A here. And when you retrieve, you just need to do a one feed-forward layer of normal neural network, or just a matrix multiplication to retrieve the associated item given the query A. Even with the query A, you can retrieve the it associated B. And in Hopfield network, the retrieval process is a bit more complicated, because you use recurrent neural network to retrieve it iteratively. And thanks to that recurrent mechanism, the qualities of the retrieved piece of memory is much better. Yeah, so basically the memory, the ability to retrieve the item is much stronger in Hopfield network. And yeah, this linked to the concept of fast weight, as the Professor Chuen mentioned before, because the memory, you can view it as a fast weight because it contains dynamically trained over time. It's very quickly and embed the information of the input and output and or BNA here to outer product, right? Yeah, so early work on reasoning try to focus on rule-based reasoning with associative memory. For example, they try to encode the set of rule, like if A is 1, B is 3, and C 4, then we have the statement X. So we need to store them in some form of memory, and later we need to infer the new rule, or infer, or just pass a new statement. And the key idea is that you can represent X entity or X item, A, B, C, and their values 1, 3, 4 as vector, and then they use outer product to bind them, and use some superimpose, maybe summarization, or take the mask operation to create a version of the memory. And then they use normal, as I mentioned before, forward parts to retrieve the output given the new variables. That is very early work on the use of associative memory in rule-based reasoning. Reason's work is much more advanced, especially with the advance of memory augmented neural networks. The idea of memory is much more clearer, because we can separate the computation and the storage. If the neural network is treated as a CPU, then the memory, we have like just the RAM, to support the CPU in this computation. And we have the computers that learn from examples here. So one of the first work on memory augmented neural network, or MANT, is a neural Turing machine. Here, the memory is just a 2D matrix, and its controller is the neural network. Everything is trained end-to-end, and it simulates the behavior of the Turing machine. So it can support symbolic reasoning, and it supports algorithm solving. You can look at the graph on the right-hand side, and you see the basic operation of the memory. First, you give the memory a sequence of input. Yeah, maybe in this case, it's a sequence of binary vector. The input comes to the controller, which is a neural network. The controller sends the read and the write signal. Yeah, you can see it's first it sends the write signal, to store the input to the memory, then it sends the read signal, basically the attention to read the content from the memory to produce the output. That is how it operates. And when you look at the detail, you can see that the controller, which is a neural network here, takes the input and it's produce the controller output, which is the addressing parameter, and it's produce a memory parameter to basically it is the content that need to be written to the memory. I will not go to the detail of each step here, but you can see that it goes through many steps of refining the address where we should store the input to the memory through many kind of like mechanism, like we store based on the content, we store based on the location. Then we find out the weight here. The final weight is the address, kind of the address that we want to store the information. And given that address, you can write to the memory and or read from the memory using normal attention. So that is really a breakthrough in 2014 when the works were introduced, because for the first time we can kind of like separate the memories and computation by using neural network, of course, and it's basically the motivation for the design is the author try to simulate the memory addressing mechanism of Turing machine. So it's really cool paper. Yeah, so when we talk about memory and its operation, writing or reading, so the question is, what is the optimal memory writing for better memorization? I think it is easy to realize that if you write too much or too often to the memory, it will destroy the content of the memory because the memory size is always finite, right? So we want to know, given an input of sequence length t, and we have only d writes, when should we write to the memory? And it turned out that, the theory suggests that uniform writing is optimal for memorization. You can find the details in the paper here, but we can prove that it's best to write it to write it uniformly by it's like equal interval, and then you can achieve the optimal memorization. And when you have better memorization, you will have more capability to do reasoning. In this example, we give like algorithmic reasoning as an example, and you can see that with uniform writing, the content that is written to the memory is much more clearer. It is not blurred as in the regular writing, and also like because you write better information, so when you decode, you can read better and you can do reasoning better. So that is the optimalities of memory writing. Another form of item memories is memory of independent entities. They are a bit different from the concept of memory augmented neural network because they treat each slot of the memory separately. So which means the memory writing is done separately for each memory slot. So when you write some information into some slot, it doesn't interfere as a slot. And you can think of it as like each slot will maintain the life of one or some entities, and they are independent. And the memory can be implemented as a set of n-parallel RNN, recurrent neural network, like this one. Yeah, so the first INN, the hidden state of the INN store the Apple and John as entities, and over time, it will encode other entities like office and kitchen when it's read through the fact in the baby task here. So when we have more facts, then the memory slot is added with more entities, and we maintain that over time. The second INN can store the same entities, but maybe with different order, so with different focus. The first INN may focus more on John, but the second INN may focus more Apple. So when they meet the questions like where was Apple, they know that it's in the office. And this is over time. Okay, the memory slot is updated over time. They just updated separately. So the ideas is implemented in a recurrent entity network, and you can see that they are just a set of parallel INN with a hidden state update over time, simulating the life of an agent. And when you read more fact or you read more sentence in the document, you update the hidden state of each INN using gating mechanism, of course. And finally, when you have the query, where's the ball here, you multiply it, dot product here, with the final hidden state, and do attention, to get the final output. Y was in a garden, for example. A recent update of this kind of memories can be found in a paper called Recurrent Independent Mechanisms. This paper focused more on the disparities of the attention between the entities. So you can see that the idea is quite still similar. You maintain a set of parallel recurrent network here. So x square here represent one INN, and the interaction between the INN can be used, can be materialized by the attention mechanism, but it should be sparse. And over time, we can update the hidden state as well as perform the attention to compute the relationship between the INNs. As you can see here, we update the hidden state using the STM, and we use attention to capture the relationship between the INNs. And another attention also is applied to capture the input, or just about the input reprocessing. But the key idea here is you also want to maintain the life of the entity through each INN, and you allow it interact with each other through attention. So that is all about the item memory section. I think before moving to the relational memory, if you have any questions or any comment on the item memory part I just presented, please give me, please ask questions. Anyone have questions or have something to share? Okay, so if not, then we can move on, and you can just jot down your comment or any question on the chat, and we will look at it later. So the second type of memory is a relational memory. Okay, so in the relational memory, we have a different motivation, because item memories is normally weak at recognizing the relationship. Item memory is just about storing the item, right? And it's very hard to relate temporally distant item using this kind of like associative operation like this one. Then if the item memory cannot store the relationship, it's very hard to do the retrieval by inference. Like if you see a woman A in house B, and you see a man C also in the house B, how do you know that woman and the man have some relationship? This kind of question is very hard to answer in item memory. Then there's a similarities, as I mentioned, between memory and reasoning. So in memory, there's also dual process, which item memory represents simple low order system one, so it store item, and relational memory is store relationship between the item. So it's very complicated, it's high order, and it represents system two. You can see, yeah. So the item is the first layer. It store the item memory is the first layer. It store different item A, B, C, and the relational memory is the second layer. It stores the relationship between the item. One way to implement the ideas is you implement the memories as a graph. So using graph, memory is a static graph with fixed nodes and edges. And the relationship is clearly encoded in the edge of the graph. But in this case, because the memory is static, so basically you somehow know beforehand which is the relationship. And the X node in X memory slot or X memory node store the state of the graph node. You can perform the writing to the memory using message passing or graph attention or any mechanism. And you can read from the node using the multi-layer or feed-forward neural network. Yeah. Here I give an example of like the message passing here. We can create a message based on the hidden state of the node between the two nodes that share the same edge. And when you want to read from the memory, you do the you do the reading as usual here. You sum up all of this message from the neighbor node, and then you use some function G or from neural network to read to update the hidden state of the node, and also to give the output. And these kind of ideas can be used in reasoning tasks like the baby datasets or clever datasets. So in baby, for example, they encode node as a fact in the text. So each fact or each sentence have some embedding and used as a node. They use some LSTM to create the embedding of the node. Yeah. Also the query, the information of the query also encoded into the node. The edge, sorry, the information of the query or the questions encoded in the edge in this paper. And finally, yeah, the answer is read out using the mean pooling of all the hidden state of the node. Yeah, the idea is similar. Still, you message passing to update the hidden state of each node, and it can achieve very good results on the baby task. Similar performance can be found for clever datasets. For the clever datasets, you are given a kind of picture like this, and you try to reason about the position, the location, the color, something like if the green jump 3 steps, then yeah, which is plus. Yeah. Again, in this kind of memory, you need to have a clear definition of the node and the edge. And normally you have to design it based on the problem. And the performance of the, this kind of graph-based memory, normally it's much better than the relational network or normal INN or MNP network. Another type of graph memories is the conditional graph memory. So in this model, they encode multiple graphs. Each graph is stored in a set of the memory row. And for a graph, the controller read and write to the memory using the attention, or reading using the attention and writing using the message passing. And the output is again aggregated from the read vector from all the graphs to create, to produce output. So besides using graph to capture the relationship, there can be another way. And the obvious way, or the most straightforward way, is to use the attention mechanism. This is much convenient because the graph memory needs customization to the task, and you need to design it carefully. But if you just use a generic form of the 2D or tensor memories, you can use the cell attention mechanism to capture the relationship. As you can see here, this is just a visualization of the cell attention process. But the idea here is that each memory slot represents an item. So if you do cell attention, you are capturing the relationship between the memory slot, right? And you can update the memory using that cell attention output. And the paper named Relational Memory Core do exactly the same. They employ the cell attention mechanism to update the memory over time. When they have a new input, they just append it into the memory slot here to create a new slot. Then they use a cell attention mechanism to reduce the new memory to the original size memory. So even though here you add a new slot, but later the updated memory still remains the same size. And yeah, the detail of the update or how they use the memory for reasoning tasks, you can have a look at the equation here. But basically, it's just like, other memory augmented neural network where you access the memory content and you try to use it for the task. And using this kind of memory with cell attention to capture relationship, you can answer a lot of questions. For example, given a set of vector, you can answer sub-question like, what is the end farthest from the vector m? And performing attention mean you're trying to compare the vector m with all the vector in the set of vector, and you, based on the similarities or based on the distance, we can find out which is the furthest or the end furthest. That is the basic. That is a perfect example for the use of cell attention in a capturing relationship. The cell attention is dot product, right? So the dot product attention can work for simple relationship. And in this case, if you have some like animal like this one, and you have a query like which is a cat, and it asks what is the most animal similar to the cat, you can do dot attention, compute the cosine similarities between cat and other animals, and you find out, that is a tiger. However, for difficult relationships such as what is the most similar animal but not the tiger, then dot product attention seems not rich enough because it's only contains one scalar to represent the relationship. So it's not rich enough to demonstrate the multivariable relationship like this kind of questions. So we can conclude that for hard relationship, scalar representation is very limited. So that comes a more like higher order memory, relational memory. Here, the cell attentive associative memory. The picture looks very complicated, so I don't want to go into the detail, but here you can grasp the basic ideas is you can use an item memory MI here to produce a relational memory MI here. And this simulates the dual process that I mentioned before. The item memory can be a 2D matrix, but the relational memory should be like 3D or higher, because the relational memory basically is stored relationship. So the relationship here is represented by the outer product between two items, not the dot product as in the previous work. So that makes the relational memory very high dimensionalities. Yeah. And of course, when you put the two memory together, you need to care about how they operate, how they transfer the data, and how you get the output from the relational memories. So all of these details can be found in the paper and in the equation here. Okay. That is the complicated details. So let's have a look at some motivation or some illustrative example. So given that you have an item memory, you can extract the item, right? And you can associate every pair of them using the outer product to create like a 2D matrix for each relationship. Because it is 2D matrix, so it's very rich, much better than the scalar dot product. And you can stack all of these relationships to form a 3D relational tensor, and it makes the relational memory. So that is the idea of this paper. Okay. Yeah, we have the final part in the memory section, which is the program memory. Do you have any questions regarding the relational memory part I have just presented? Okay, so if not, then yeah, let's move on to the program memory part. Here I will cover just like the module memory and the store program memory. Okay. Yeah, there's another very interesting concept is the module. So a program, if it's designed for a task, it's become a module. And in the paper named the neural module networks, the authors try to construct a set of modules. Each module is aimed for some specific task. And to know the order of the module execution, they pass the questions to produce a module layout like this here. Given a input which is an image, and given the questions where is a dot, you have a parser to create a layout of program execution. Each program here is a module or a neural network. So the output of one neural network will be the input of the another neural network. And the question is how to learn the weight of each module to master the task or to answer the questions. The program selection is beyond the parser, right? So you need to pre-train the parser. Other things are trained end-to-end, and they design five type of modules, which is designed for different type of tasks. For example, like attention tasks, labeling, create label, classify tasks, measurement tasks, or combining all of them. So by combining the five templates together, the final model is very powerful and can answer a lot of questions. And they need to use some NLP parsing tool to pass it into the part here, as you can see. Another ideas, which is similar but more generic, is ideas of like program memory. So here, the most powerful memory is the one that stores both the program and data. This principle is known as the store program principle, and has been mentioned in the Universal Turing Machine or Harvard and von Neumann architecture. So we need to break a big task into subtasks, and it can handle by a Turing machine store in the program memory. So the program memory will store the Turing machine. And one neural implementation of the ideas is a universal Turing machine. It tries to select the program or the neural weight by the program attention. So the program memory store the key, which is the address of the program, and the values, which is the weight of the program. And the weight is selected and loaded into the controller of another neural Turing machine. So the whole architecture simulates universal Turing machine, right? And everything is trained end to end. You don't need to design the modules, or you don't need to design the program at hand. Just let the model learn end to end. And the key is the program attention, which is very similar to the normal attention. It's just performed on the program or the wait space, not on the like activation space. Another idea related to the program memory is the ideas of like how we can break a program into a mini programs. In prior work, one program equal to one neural network with millions of parameters, which can be very hard to scale if you want to store like hundreds or thousands of programs, right? And also it very parameters efficiency, since the programs are separated, they're different neural network and they do not share common parameters. So the solution here is they try to store scalable mini programs to compose the infinite numbers of the real programs. And you can think of it as like you building the Lego structure. You're building a big Lego structure based on basic Lego bricks from a set of possible, mini programs or the bricks. And the construction of the big program is dependent on the input. This paper also introduced one concept like the recurrent program attention to retrieve the singular components of a program. So the mini components of program is just the singular component. So you use a SVD, kind of SVD, or you use to break it into like singular values, singular vectors. They store them on the memory, and they retrieve them to compose the program or the weight, as you can see in the equation here. Yeah, and the results is very promising because you can see using this mechanism, you can detect the task boundary even when the task ID isn't provided to the model. It can still learn to attend to the correct program or mini programs when the task change to a new one. And interestingly, the program attention mechanisms is equivalent to the binary decision tree reasoning. So you can use the architecture to classify the image like the MNIST datasets, and then the pattern of attention to the program represent or resemble the binary decision. And the parameters of the model is very small as well. Because the memories, the program memories only store the mini program, so they are very efficient and fast to train. Okay, so that is the last part of the memory section. Do you have any questions regarding all of these materials I have been talking so far regarding the memories, item, relational, or program memory? Anyone want to talk or ask me something? Okay. So if not, then yeah, let's move to the final part. Which is, I think I will go through this one quickly because it's a new, but it's just a small new domain in reasoning, which is a combinatorics reasoning. And I will show you guys how people using INN or memories or graph transformer to do this combinatorics reasoning. Okay, so the motivation is how can we implement combinatorial algorithms with neural network? The algorithm can be the traveling salesman problem or the sorted path problem, the maximum spanning tree problem. So any graph or any traditional classical algorithms, can we solve them using neural network? So the aim is to train a neural network P to imitate an algorithm A. And of course, the neural network P or the neural processor P is aligned with the algorithms and it's gradient or trainable because they just neural network, right? And unlike the classical algorithms, the neural processor B can extend or to generalize to natural input. So it can work with real data. F and G here is the encoder and the decoder function. So after you train with the processor B, you can just train the encoder and decoder function to make it work for different data sets. The first example is using the INN as the processor. The processor is INN, so which means you use a recurrent network to encode the problem, and then you try to cheat the input at a sequence. Treating the input at a sequence is actually not easy and it's very hard to generalize, especially on graph problem. But the strength of the INN is it's Turing complete, so it can simulate any algorithms in theory. But again, it's very hard to learn from the data. And one example is the Pointer network here. They can learn up to like 50 points on the problem like the convex hull or the traveling salesman problem. But other than that, longer than that, it's really hard to learn. And the idea of the Pointer network, I think, is very common still, using the attention to point to the input, to point to the item in the list or in the sequence, which is a node of the graph, to point back to the node of the graph at the answer. And also you look at the memory complexity and the computation complexity. This kind of approach is not really efficient. You can also use processor at the MAN or memory augmented neural network. The big advantage of MAN is assume finite memories with O1 actually, not scaling with the data, and it's only require ON computation because you attend to a fixed size memories. But again, it still need to sequentialize the input, so there's no assumption on the input structure, which is a big disadvantage. People manage to make memory augmented neural network usable for tasks like graph reasoning, like finding the sorted path, and also like playing games, board game here, or doing reasoning on the family tree. The interesting part is the data, even all the data is synthetic, but it can generalize well to the real world data. Because, as I mentioned, the memory things, they simulate the Turing machine. So if they can learn the algorithms of the Turing machine, then it can generalize very well. Another one extension of the idea of memories for combinatoric reasoning is using the program memories or the neural universal Turing machine, which I presented before. You can see that the neural universal Turing machine can solve multiple algorithms as one. You can give the model a sequence of algorithms, and it can learn to switch from the program to another, to choose the correct program for the algorithms, and solve all of them perfectly. Yeah, and the performance compared to the neural Turing machine, when you increase the number of the programs, is also clearly demonstrated here. The loss convert much better for the NUTM here. The relational memories, which I presented earlier, also can be used for graph reasoning, right? Because the relational memory basically it captures the structure and it can be applied to graph problem. And actually, in the self-attentive associative memory, the author tests it with different combinatoric problem like convex hull, TSP, shorty path, and minimum spanning tree. Yeah, and the performance compared to other INN or MAN processors, yeah, you can see that they're huge improvement in the performance because the advantage of using relational memory. Okay, so the best, I mean, not the best, but the most natural way to design the processor for this kind of problem is using graph neural network, because most of the algorithm or combinatoric problem operate on graph. So if you use a graph neural network as a processor, it perfect, fit into the problem. So for the graph neural network here, you can use different type of supervision to train the graph neural network for algorithms. And the basic architecture is you have an encoder to encode the graph. You have the process, which is the graph neural network processor to process, and you have the decoder, which is the M and P to produce output. As usual in many graph neural network problems. Yeah, as you can see here, every node in the graph have its hidden stage, and you need to do some operation on the graph, maybe attention or massive passing to encode the Z, which is the embedded version of the node, and the edge to perform the the massive passing to update the hidden state, and then you use the hidden state to produce output for the node, and also produce a termination signal for the algorithms. One example is a problem of DNF counting, where we try to count the number of assignment that satisfies disjunctive normal form formula. And you can see here, you can represent the formula in the form of the graph here, and you perform the massive passing from the leaf node to the middle node, from the middle node to the root node, and propagate back the information of the message to update the hidden state of each node here using the massive passing. And this kind of massive passing for graph, when you use, is only take like linear time complexity compared to the classical algorithm, which is polynomial time. And people also rely the alignment between the neural network and the algorithms, because you can see, for example, like there's many algorithms of many problems, right? And the most basic neural network is multi-layer perceptions. It actually people realize that it's not it's not related to any kind of like algorithms, because the form here is really hard, to use the MMP to solve the algorithms. But for the other architecture like the deep set or the graph neural network, it shows very high correspondence between the algorithm type of summary statistic or relational type of algorithms or even dynamic programming. For NP-hard problem, of course, there currently no architecture that can fit in this very hard problem. But one recent paper tried to approximate that with a neural exhaustive search, right? So to make it clear that how GNN is aligned with the dynamic programming, you can see that the operation of a graph neural network and the operation of a typical algorithm, which is the Bellman-Ford in shortest path finding. You can see that the massive parsing here is very similar to the dynamic programming update. The hidden state is a kind of like the intermediate results that need to be updated over time. And the passing from the neighbor is something like you updating with the cost of the neighbor of the current node. And the results look very good for the graph, neural network as a processor to solve problem like shortest path or dynamic programming. Compared to deep set or MNP, graph neural networks is always better. Another type of supervision in graph for reasoning, combinatoric reasonings, is you directly supervise on step level. You merely simulate the classical graph algorithms. So when you run the classical algorithms, you have the temporary results here, and you use that as the label to train the graph neural network. In this case, you can only simulate the algorithms, and there's no new algorithm discovery. But when you can learn, it generates very well. And the author suggests that we can do multiple algorithms learning all as one, and it helps boost the performance further. As you can see here, they try different kind of graph neural network, massive parsing, attention, and it can generalize far beyond the training set of 20 nodes, but it can, up to 100 nodes. The final architecture is the processor as transformer, which is expected, right? So it doesn't treat the input as a graph anymore. Rather, it treats as a set. Because transformer work on the set. And here, they use an encoder mask to make the set kind of like a graph, because when you mask some node, which means you assuming that the other node have some relationship. And the author used this kind of idea to apply the transformer on graph combinatoric problem. Mask encoding, then the normal decoding with the binary representation of the number. And more importantly, in the decoding, they output the pointer and also the mask for the next step. So these two kind of output make the problem, make the architecture is recurrent and very dynamic, as you can see here. And they train the architectures with execution trace. For example, if you're trying to build to simulate the find mean subfunction here, you need the ground truth of the mean index and the mean element to train this find mean architecture. So you need this level of supervision to train the whole system. And the results again show very strong generalization, even when they don't assume any like structure or graph in the input, which is very amazing. Yeah, you can see that on the problem here, compared to the vanilla transformer, the vanilla transformer performance drop over time, the green line here, but their method, persistent and keep the, like almost perfect performance over time, even when the length of the test sequence up to 100. And when you look at the attention pattern, yeah, the attention pattern very clear, even when you generalize to longer sentence, longer sequence. And yeah, when they test it with sorting, multiplication, and many different algorithms, the visualization of the unseen data and also the seen in the training also indicate that, yeah, the embeddings show very consistent and coherent structure even when they're not seen in the training. So they claim that they learn very good embedding of the input. Yeah, so that is all for my section today. Regarding the part on the combinatoric reasoning, do you have any comment or any other questions you want me to discuss more? Okay, so yeah, so I think we will have a break after this section before moving to the next one, right?
Yes. So I would thanks. I would suggest we have like half an hour's break before moving to the next part.
Yeah, sure. Okay, so I'm
okay
stop sharing and yeah, see you guys in the next 30 minutes.